everybody. Welcome to AP Chemistry video. Okay, so this is Mrs. Hanson. Today I'm going to try to keep this really brief. We are going to learn how to write net ionic equations. The whole purpose of this is just to write normal chemical reactions, balance them just like you always have, but we're going to focus on the parts of the reaction that are actively reacting. Okay, so it's just a couple more steps from what you normally know how to do. Okay, first step. Let's just do an example. It says aqueous solutions of silver nitrate and potassium chromate react. Okay, so if you look at these three bullets, the first step is to write out the balanced molecular equation with states of matter. That's just doing what you normally do. So let's try it. Silver nitrate. Okay, now this is weird. Okay. Please do remember that your compounds always have to be balanced. So Ag plus, remember silver is always a plus one. Nitrate off your polyion list. If you don't have your polyion list, you better get it. Okay, so AgNO3. Okay, and it says right here it's aqueous, so I'm going to put an AQ next to it. If you didn't know if it was aqueous or not, if it didn't say that, that's what your solubility rules are for. So while we're getting your polyion list out, you're going to want your solubility rules as well. Okay, and all nitrates, silver nitrate included, are soluble or aqueous. Okay, so reacts with potassium chromate. Now this step right here, you don't have to do it, but it's definitely helpful to make sure your compounds are balanced. Okay, so K2CrO4. Okay, so it says it's aqueous, so I'm going to go ahead and put aqueous, but you should be able to look it up on your solubility rules and confirm that. Okay, so predict the products. Well, no surprise here. Compound reacting with compound. This is going to be a double replacement. Okay, so we're going to go ahead and write out the balanced products now. Okay, so silver's hooking up with chromate, Ag plus, CrO4 2 minus, so it's Ag2 CrO4. Okay, and then potassium's hooking up with the nitrate. Okay, and they're a plus one and a minus one, so KNO3. Okay, so what are the states of matter for these guys? Go back to your solubility rules. Okay, so let's see here. All nitrates are soluble. All alkali metal compounds are soluble. Okay, so that definitely means that the potassium nitrate is aqueous. That's an AQ, by the way. Now, what about the silver chromate? So we go back to the solubility rules. Let's see, what's it say about your chromates? Okay, so pretty much says all silver, lead, mercury salts are insoluble unless bonded to number one, really should be number two, nitrates, acetates, blah, 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 blah. So basically, silver is, for the most part, usually insoluble. So guess what? Instead of putting an aqueous by this guy, we're going to put an S for solid, an S for not soluble. Okay, well, now the fun part. So rewrite the balanced equation, splitting up any strong electrolytes. So with your solubility rules, you also got to be going over what your strong and weak and non-electrolytes are. Okay, so you remember SAS, strong acids, aqueous salts, strong bases are strong electrolytes. Okay, so what that means, I want you to focus on the A here, aqueous salts. Okay, so you know what? If you look back at one of these salts, the silver chromate, it's solid, it's not aqueous. Okay, so these guys are all going to split up. This guy is not. So what's it going to look like? So let's see, Ag plus and NO3 minus. All ionic compounds split up into their ions, right? Okay, now this guy here, two potassiums, so 2K plus. And actually, before I get too far, there's a step I forgot. We probably need to go back and balance this molecular compound, or this molecular equation. So let's see, two silvers, so I'm going to put a 2 here, two nitrates, so I'm going to put a 2 here, two potassiums, we're good to go. Sorry, I forgot that step. So now when I balance these, I'm going to incorporate that. So we'll put a 2 here, put a 2 here because of that coefficient. All right, so this guy's going to break up as well. But this time, two potassiums, so 2K plus, and then the one chromate ion. Okay, notice that when they break up, you definitely have your ion charges. All right, here's the big one. This guy is a precipitate. It's a solid. It is not aqueous. So guess what? It does not break up. It is a non-electrolyte, or at least a very weak one. So we're going to leave that labeled as a solid. This guy's going to split up, so 2K plus 2 nitrate. Okay, now technically you could go back and label all these things that broke up as aqueous, but we're not going to bother because we're not done yet. Okay, now here's the really fun part. This third bullet says cross out any spectator ions. just like when you go to the soccer game or the football game, the spectators are just the ones sitting up there in the stands like bumps on a log. They're not doing anything. Okay, so spectators in chemistry are things that don't change from the reactant side to the product side. So let's see, what spectators do we have? 2Ag plus. Okay, well here it's locked in this compound. The silver changed. It is not a spectator. Okay, 2NO3 minus. 2NO3 minus. Okay, those totally match 100%. Spectator. Spectator. Bye-bye. You cross them out. Okay, 2 potassium plus, 2 potassium plus. Those are spectators as well. They have to be an exact match on the reactant side to the product side. All right, bam. Now we're just going to do a little rewrite here. So what do we got here? 2Ag plus. I'm going to go back and put the states of matter in there. So aqueous plus chromate, aqueous, and then yields or produces silver chromate, solid. All right, so that's a double replacement reaction. We're going to call it a precipitation reaction because two aqueous components reacted to produce a precipitate, or to produce something that was not soluble. What do you think? You think you can do this? Well, let's give it a go. So we got a couple more examples. This time I want you to go ahead and pause the video. Okay, not yet. Let me give you instructions. And go ahead and write out the molecular equation. So that means just write out exactly what you would have done in CP Chem. Make sure you put the phases in. So go ahead and pause. Make sure you pause and go ahead and write it out. Okay, hopefully you paused. Let's see if this is what you got. Okay, so aluminum solid, aluminum metal, reacting with hydrochloric acid, HCl. Acids, by definition, are things that they have to be dissolved in water. Okay, they only become acidic when they're dissolved in water. So all acids are always aqueous. Okay, and then we made a classic single replacement reaction. This aluminum hooks up with the chlorine. We made aluminum chloride. I made sure to balance that, and that's aqueous too. How do I know? Because there's all this water from the HCl, right? And ionic compounds, okay, are going to be aqueous if they're soluble according to the solubility rules. Okay, and it says here all chlorides are pretty much soluble unless bonded to PMS, lead, mercury, or silver. Not the case in this example. So that's aqueous. Okay, well, what about the hydrogen gas? Okay, that's going to bubble away as a gas, so we'll put the label for G, okay, to represent the gas. All right, let's break up any strong electrolytes. Well, aluminum's not going to break up. HCl, going back to the strong electrolyte list. Strong acid. Bam, it's going to break up. So H plus Cl minus. Okay, silver chloride. It's an aqueous ionic compound. It's an electrolyte. It's going to break up. Make sure you got that 3 right there because there's 3 chlorines. Okay, and last but not least, hydrogen gas is not an electrolyte. It is not made up of ions. It is not going to break up. Okay, now of course you guys forgot to remind me. I forgot to balance this compound, so we got to backtrack a little bit. Okay, you guys probably did that. So let's see here. 2 in front here. Let's make sure I do this right. 6. So put a 6 here. 3 here, 2 here. So now I got to go back and incorporate that. So 6H plus, 6Cl minus, 2, and then, this guy actually becomes 6. Oops. Sorry. Okay. There we go. And this guy is going to hang pretty at 3. Okay. Now, let's see. Do we have any spectators? Things that are exactly the same on the reactant side as the product side. I hope that you guys see that we have, looks like 1 spectator. Cl minus, 6Cl minus. All right, guess what? We are done with that one. And you guys can go ahead and rewrite it. So 2 aluminum solid plus 6H plus yields 2 aluminum plus 3 plus 3H2. Okay, and I'm going to go back and put these aqueuses in there. All right, you know what? You should check. Is it still balanced overall? 6 H's, 6 H's, 2 aluminums, 2 aluminums. We are good to go. Okay? You guys getting the hang of this? All right, well, I want you guys to do the same thing for this one. Go ahead and write out the products and the reactants, okay? See if you can figure out what reaction type it is. All right, so I'm going to pause. You do that. All right, hopefully this is what you got. So ammonium hydroxide, potassium nitrate, aqueous, aqueous, ammonium nitrate, potassium hydroxide. Both those guys are aqueous as well. If you didn't know, go back to your solubility rules. Whoops, solubility rules, and it says all alkali metal compounds and ammonium compounds always soluble. No exceptions to it. Likewise, your alkali metal compounds are soluble as well. Okay, so aqueous and aqueous. Hey guys, this one's kind of a fun one. Go ahead and break up all your strong electrolytes. Okay, so I want you to do that. Anything that's going to break up into ions, anything that's a strong electrolyte, break it up. So NH4 plus, plus OH minus, they broke up. K plus, NO3 minus, they broke up. It's so sad. No date for homecoming. Just kidding. And then break up. And last but not least, break up. Well, as it turns out, everybody broke up. So how many spectators you got? Let's see here. Spectator, 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 and spectator, spectator. Everybody's a spectator. So guess what? This reaction really did not happen. Okay, we would say that this is a no reaction. Okay, meaning, you know what? All the ions are just kind of swimming around in solution. Okay, so there's no change in what's going on here. Okay, so a lot of double replacement reactions actually don't really occur. Okay, so we would call that a no reaction. So that does happen from time to time. All right, we got just a few more examples. You guys are doing so great. This one, sulfur trioxide gas. So sulfur trioxide gas. Trioxide, tri means three. It's a gas. Guess what? Gases are never strong electrolytes. Okay, and it's not ionic. It's a covalent compound, so it's not going to break up. Doubled into water. Let's see, what about water? See, all nonmetals, covalent compound, that is a non-electrolyte. So I'm going to go ahead and label it as liquid. Okay. Produces. Well, we haven't really talked about this reaction type, but I'm going to tell you that it's a synthesis reaction. Furthermore, I'm going to tell you that a strong acid is created. Let's see. Some H. We know it's got to start with H. Some S and O. Let's see if I put those O's together. You know what? Go with your gut feeling. This makes sulfuric acid. So the H plus balances out with the sulfate, and we end up with H2SO4. Aqueous. Okay, that looks great. Let's make sure it's balanced. 2, 2, 1S, 1S, 3 O's and O, 4. This is actually a reaction type that you're going to learn soon. We call this a nonmetal oxide. Non-metal oxides dissolve in water to produce acids. Okay, so we'll get used to that, and they're usually sort of common sense. But how do we do the net ionic? Okay, well, let's see. Non-electrolyte. Water, H2O, that is not an electrolyte, so we're going to leave it alone. But what about the strong acid? Absolutely, sulfuric acid is going to dissociate or break up. Here's the funny thing about H2SO4 is really the way it works. The first H comes off 100%. That's what makes sulfuric acid a strong electrolyte. You know, the rest of it, actually, that second H really doesn't come off all that easily. So I'm just going to break off one of the H's. This is how I would dissociate sulfuric acid. Okay? Everybody else stays the same. So, do I have any spectators? That is a 3 right there. Right, 3. Do I have any spectators? Is there anything on this side that's exactly the same as this side? Doesn't look that way. So this is completely done. So, yay! Whoops. That looks good. All right, last one. Sodium metal reacts with acetic acid. So acetic acid is going to start with H. Okay, acetic acid, I ate something icky, is going to come from the acetate ion. C2H3O2 minus. Okay, so I'm going to go ahead and pop that H on the front. Looks something like that. Okay, sodium metal, of course, all metals except for mercury are going to be solids. And acetic acid is an acid, so we'll mark that as aqueous. All right, the reaction type. Let's see. Metal by itself, element by itself, reacting with a compound. Sounds like a single replacement. Okay, so the sodium being a metal is going to hook up with the non-metal part, and we're going to kick out the hydrogen. Okay, so sodium acetate is going to be the new couple on the dance floor, and then hydrogen gets the boot. Okay, well, is that how hydrogen exists as an element? No. Of course, hydrogen's part of Hunkelbrief or Brinkelhoff, so let's put it as H2. All right, so what about states of matter? Well, H2, of course, is a gas, okay? And sodium acetate is aqueous, okay? It has that sodium ion. Anything bonded to an alkali metal is going to be aqueous. All right, how do we break this guy up? Well, naturally, oh boy, did I forget to balance it? Two H's, one H, put a 2 in front. Two H's, two H's. Two acetates, going with two acetates. Two sodiums, two sodiums. Look good? All right, so let's go ahead and break this up, break up all the strong electrolytes. So sodium is just sodium metal. It is good, it is fine the way it is. Acetic acid, uh-oh, go back to my list, not that list. Acetic acid, okay, that's a weak acid, so, or sorry, it's a weak acid, so it's a weak electrolyte. Okay, they do break up a little bit, okay, but we do not in this net ionic reaction ready process break them up. Okay, we only break up strong electrolytes. So I'm going to keep the acetic acid together. Okay, leave leave the aqueous on there. All right, but this guy, that's one of my ionic compounds that are going to dissociate 100%. So 2Na plus plus the C2H3O2 minus ion. Okay, so aqueous and aqueous. And last but not least, of course, the hydrogen's not going to break up. Okay, it doesn't have any ions in it. Okay, do we have any spectators? Sodium, sodium plus. These are not the same. Okay, the sodium definitely changed here. It's sodium metal, whereas over here it lost that electron and it's Na plus. Totally different. So please do not consider them spectators. Okay, and actually this guy, the acetic acid, the acetate, and the H are stuck together. Can't cross that out with this, so not exactly the same on both sides. So guess what? There's no spectators. So this is the net ionic equation for this reaction. All right, woo! I hope you guys enjoyed that. I'll give you guys one more tidbit of information. Speaking of Hunkelbrief, hydrogen's a gas. But what about the halogens? Okay, little FYI, fluorine is a gas. Chlorine is a gas. Uh-oh, bromine is actually a liquid. It's one of the only liquids on the periodic table along with mercury. And iodine, you probably do remember this because we've done some labs with it, is a solid. Okay, so people tend to miss that all the time, so I wanted to throw that out there. I too, by the way. All right, thanks for listening. You guys are awesome. Sorry this is so bumbled. Thanks for listening. What I want you guys to do now is do these two examples. Come in tomorrow with these examples done. And then you guys can compare with your neighbor and we'll go from there. All right, thanks a lot. Have a great day. Bye.